pueden ayudar aquí. Aquí un poquillo de este perro. Can you hear me? Yeah. Okay.
Não é o melhor sistema.
Obrigado. Hi, everyone. First of all, I want to thank the organizers for the opportunity. I developed this work recently with my collaborators from Federal University of Pelotas. And we revisit the question about the stability of strange stars, which I'm going to explain this kind of compact object. I'm going to give my motivation, and then I'm going to review some classic results and the state of the art results for this compact star. And then I'm going to present our results, which we are writing the paper. And finally, I'm going to give my conclusions. As you know, in the year 2020, this work was very famous because they evidenced, from a theoretical point of view, the existence of quark matter in the cores of neutron stars. And the main idea was that they were using, for instance, perturbative QCD at high densities and chiral effective field theory at nuclear densities. And they made extrapolations in the intermediate densities in order to build an equation of a state. And they found that it might exist a kind of first-order phase transition in intermediate densities. And this tells us that massive neutron stars could have quark matter cores. And these quark matter cores are more or less half of these stars, for instance, 6 kilometers, 7 kilometers, depending on the variations on the speed of sound. Okay? So I want you to remember that a neutron star has more or less 15 kilometers of radius. And if the quark matter core is 6 or 7 kilometers, we know that this radius is half of the star. Okay? And we want to use this idea in order to study other compact objects. For instance, in the famous mass radius diagram, we found the hybrid stars or neutron stars, which these people found, for instance, using these results. But if we go to lower densities, we can find another family of compact stars, which are the so-called white dwarfs. And this solid line represents stable configurations, okay? And this dashed line represents other kind of stars which are not stable. So our question was to imagine a kind of white dwarf containing a core of strange matter or quark matter in general. And for that, we look at the past works. And in this case, for instance, the first work studying this object was proposed by Glendening, Kettner, and Weber, these famous guys. In 1995, they studied this kind of idea. And they found that if one combines some white dwarf material with a strange matter material, we find that these kind of stars could be stable in some region of masses. Okay? And for instance, they use an equation of a state, pressure versus energy density, using the white dwarf material is built using the BPS equation of a state at lower densities. And at high densities, one can use the usual MIT back model. And one can vary the transition between nuclear matter and quark matter. And for instance, these values are the values of the density of transition. For instance, this value represents the neutron drift density, which is the highest density in order to get an strange dwarf. And one can vary also lower values, for instance, 10 to 8 grams per centimeter cube. And after introducing this equation of a state in the TOV equations, one can find a mass radius diagram having a different behavior from the normal one, which I have shown here. And for instance, the dot points represent the usual neutron star family. the white dwarfs at lower densities. As we increase the density, we get these dashed lines, which, as we know, are unstable. And at high densities, we get the usual neutron stars. But if we mixture this kind of equations of state at lower densities, we get another family from point D, where we start to have a white dwarf having an increasing strange matter core, for instance. As we increase density, we get the strange dwarf family, okay? And from C to B, Glendenning and all these people proved that the strange dwarfs could be stable in this region, okay? And at higher densities, we get the usual strange stars, okay? And they get this conclusion after not only looking at this mass radius diagram, but also performing the dynamical stability analysis, which means that we are disturbing radially these stellar configurations, solving this Sturm-Liouville problem founded by Chandrasekhar. And they display this function phi, which has to do with the frequency of these oscillations, okay? N0 is the fundamental mode of oscillation. And in this plot, one can see that from point D to C, this function is negative, which means that the frequency of oscillation is negative, or the square, or the function is complex. So it means that from D to C, these configurations are unstable, so these stars explode or collapse. And now we want to look for the other configurations between C and B. And they found that this function, phi, is positive in this region between C and B. So the frequency is positive and real. And these stars only oscillate after receiving these external oscillations. So these stars, these strange dwarfs, are stable. Okay? So this was the main result. One can also vary this cross density, okay? And one can find a similar behavior, okay? This is the case of the neutron drift density. We can decrease this density, and we found more or less the same behavior. And in the limit of 10 to 9, we start to lose these configurations, okay? So there is a very small window where these stars can exist. Okay, after that, in 2017, other people, Alford, Harris, and Chasdeva, they say that this result, original result from Glendenning, was wrong. And they studied the problem again, but now using an equation of state similar, also using the MIT back model and the BPS equation of state. And their plot was like this, the energy density versus pressure. And after solving again the same equations from Chandrasekhar, they found the same behavior in the mass radius diagram. But when they plot the behavior of the frequency, they found that from A to D, from this to this, all the stellar configurations or all the strange dwarfs are unstable. So strange dwarfs cannot exist. This is in contrary to the result of Glendenning. So this was a very interesting problem because no one knows exactly what was happening. So in 2017, there appears this work related to the phase transition effects in the dynamical stability of neutron stars having discontinuities in the equation of state. And they developed a formalism where you not only solve the Sturm-Liouville problem, but you have also to impose boundary conditions on these equations because the transition is discontinuous between nuclear matter and quark matter. So these people was using not a discontinuous transition, but they were using only a parametrization, which is very soft. So they lost information doing this kind of parametrization. Okay? And that was the reason they didn't find any stable white strange dwarf. And for instance, the idea of imposing boundary conditions in this kind of stars is as follows. The we don't know exactly the microphysics between a transition of hadronic matter to quark matter, but we can study the cases where, for instance, there is a microscopic time scale where after a radial oscillation, the matter in the boundary between both phases can oscillate and can influence the other phase. And for instance, we can assume two cases that the lifetime of the reactions are very small compared to the time scale of the oscillations, or this time scale of the reactions is very large compared to this period of the radial oscillations. And for instance, in the case of this case where the time is very small compared to the period of the oscillations, we call these rapid conversions. And in this case, the conversions are too fast that when we disturb the neutron star, we don't have any flux of energy, of heat, of matter. So there is a mechanical equilibrium and also chemical equilibrium between these phases. And we can say that the variation in pressure after the oscillation occurs, the pressure is the same, okay? But the amplitude of the oscillation, which is this variable, see, it is affected because the initial situation has to be the same as the final situation, so we have to fix the behavior of this variable of oscillation in the case of rapid conversions, and it has this form. And in the case of slow conversions, we can have the opposite case. And for instance, the quark matter might affect the hadronic phase, but only mechanically. So we still have this continuity in the pressure because at the end, this oscillation lasts only for a few times, and then the oscillation goes back to the quark phase. So there is no effect on this variable. So the main thing in these boundary conditions is that there are some discontinuities to be accounted in these variables, okay, which are the variables related to the radial oscillations and affecting the dynamical stability. So quite recently, in July, there appears this work from a group in Italy and Belgium, where they consider the case of having this kind of fast conversions and slow conversions. But they consider that these effects are not affecting too much the stability of strange dwarfs. They only said that we can escape this kind of problem if instead we fix the variable number of the hadronic phase, or the quark matter phase, and we can solve the TOV equations. And for instance, in this case, they fixed the baryonic number to these numbers, and they found usually the same behavior as I have shown you, but now these continuous lines are related to exploring other situations where the baryon number of the quark phase is fixed. In these cases, where the energy density of the transition is varying, we found the usual cases, but if we include these constraints, we found some stable families, okay? So this is different, but my collaborators and I were interested not in applying this kind of solution, but only solving correctly the oscillation equations, which we prefer to use a variation of the Sturm-Liouville problem, and they are related to these variations. As I mentioned, the radial variation of the volume elements within the star, and the variations generated in the pressure when these variations occur. And omega squared is the frequency. So, and we have to impose these constraints on these variations. But now also, apart from using the MIT back model, which was used in this work and in the work of Alford and in the work of Clendening, we use, apart from the MIT back model, we use the perturbative QCD result from Kurtela, Romansky, Vorinen, and all these people, but put in a pocket formula, and which accounts for the QCD interactions at lower densities. Okay, this is the normalized pressure, and this is the equation of the state we insert into the TOV equations and the oscillation equations. What we found was that, for instance, in the case of the MIT back, when solving the TOV equations, we found this behavior in the mass radius diagram, but again variating this transition density between hadronic and quark matter. And the behavior is as usual. If we have large values of the crash density, we have this large line. If we decrease, the stability line is decreased too. We can also plot the behavior of the mass versus central pressure. And at this point, we can apply the usual criterion of the derivative of mass versus central pressure. And we can say that maybe these configurations are stable from this, the instability begins, and also from this case and all that. But we prefer to solve the oscillation equations, having these boundary conditions. And we also plot this phi function, which is related to the square of the frequency. And for instance, in this case, we study different values of the cross transition and also different behaviors of the conversions of the phases. Okay, rapid conversions are the continuous and the dash are the slow. And for instance, this case represents the highest transition density. And we found again the results of Lendening, where there is a small window of stability for strange dwarfs between this maximum to this point, more or less. So the stability is recovered. And we can vary this transition density. And we found other interesting results because depending on the conversion speed, we have the no strange dwarfs in the case of rapid conversions at lower cross transition densities. But in the case of slow conversions, we again recover the strange dwarf stability. And as we decrease this cross transition density, we recover again these kind of families. So we can study this situation using also perturbative QCD for the equation of the state of quark matter. And these values are the values of x, which are called the renormalization scale, and are related to variations in this band, for instance, more or less from this to this, because these values satisfy the strange quark matter hypothesis. And for instance, in this plot, we can see that independent, or more or less independent, on the variation of x, we recover the same results for this transition density. So the renormalization scale does not affect our conclusions in this case. And we can also recover the mass versus central pressure behavior. Again, we can apply the derivative criterion. And by looking at the behavior of the frequency through this function phi, we again recover the stability of strange dwarfs using this transition. And using the other value of x, we can recover again some strange dwarfs, stable. But in the case of x4, the window stability is smaller. Okay? So in this work, we revisit this problem because there are few works studying this kind of star. But now analyzing properly these kind of discontinuities in the stability, because these numerical calculations are very time consuming, so one has to do it very carefully. And we found that the strange dwarf family between this maximum to more or less this are really stable. Okay, so This is true for rapid and slow conversions, okay? And the main thing here, or the main physical thing here, is a so-called reaction mode. This reaction mode is not found in usual calculations, for instance, when studying strange stars, because usually in this kind of strange stars, the radius of a strange matter is more or less of the size of the hadronic mantle, okay? But in these strange dwarfs, the radius of the strange matter is very small compared to the crust. So we can perturb the whole star, the whole strange dwarf, but the oscillation of the crust will dominate over the oscillation of the core. And in some cases, this oscillation of the crust hides the stability of the core. And that is the reason why we think all these people haven't found any stability, because when they were solving the equations for the stability, they were not including the boundary conditions, and they were not looking at the behavior of the reaction mode, which is different with, in these cases, of strange dwarfs. So from our analysis, these stars are stable. And in order to prove the robustness of our findings, we use also perturbative QCD, which is another model for cold quark matter. Thank you.
Thank you, Jose, for the talk. I have a very naive question. So regarding the plots that you showed in the beginning, so shouldn't the white dwarf respect the Chandrasekhar limit of 0.4 solar masses? So in the beginning, you showed these plots for the white dwarfs, and they seem to go above 0.4.
Yeah. In this case, right?
Yeah, for example.
Yeah, in this case, we are using only a nuclear equation of a state having electrons and all that, but we are not including nuclei from carbon, oxygen, and all that. So we can improve the equation of a state, but there are a lot of models, and it is not very accepted in the community. In this compact star community, it is more accepted to use the BPS equation of a state.
So if you included these things, you expect the white dwarf to have mass below the 0.4 limit?
Yes.
And one also very naive question. So you showed in slide 20 and slide 23, for example, those wiggles in your profile. Is this physical? Like, is there any physics associated to those bumps and wiggles that you find in the curves?
Yeah, for instance, at the beginning, we thought that maybe these are related to some physical consequence, but we didn't find any explanation, but we performed the calculations many times in order to prove is this some numerical instability or not, but the results are the same, using the perturbative QCD and the back model. Okay.
Thank you.
Very simple question. I simply forgot the original papers from 90s that motivated the consideration of this kind of mixed state of matter.
Yes.
What's the evolutionary line that could lead to this kind of stars where you would have a strange matter and a white dwarf matter?
Okay. In this case, there are two explanations, or main explanations, I think. One is that a usual strange star absorbs nuclear material from a companion, and this companion is absorbed, and at some moment, this nuclear mantle gains over all the stability, creates an explosion, and the final result is a strange dwarf. Other is related to, for instance, the sun absorbing some strange nuggets, and after millions of time, this star will collapse, and when collapsing, this star will have a lot of nuggets in the interior, so you will build a white dwarf having a non-negligible amount of strange matter.
Thanks.
More questions?
Hi. You said that you use perturbative QCD to calculate the mass-radius relation in the dwarf stars, right?
Yeah.
So you are implying that inside dwarf stars there are the confined quark matter,
Yes.
and there is a transition just like in neutron stars?
Yeah, for instance, in this kind of transition, we don't know the microphysics exactly, but for instance, we only assume that the nuclear mantle will be big enough in order to deconfine at some moment, okay, at some density, and there are a lot of uncertainty because this can occur in this crash density or this neutron drip density because, for instance, if the nuclear mantle reaches this density, the neutrons will drip from the nucleus, and these neutrons will gravitate the core, and they will be absorbed by the strange matter. So this nucleus will be converted to strange matter. So the transition is not related as in usual neutron stars because we don't know, or we don't impose mechanical stability, we don't impose chemical equilibrium, we don't impose thermical constancy. We are only looking for a window where these stars could be stable, where a transition which is reasonable might occur. Okay? It is different, like in heavy neutron stars.
Yeah, I just wonder because you're using perturbative QCD, you are
No,
worried about
we are
the transition, right?
Yes, we are using only perturbative QCD as a model for quark matter, which can be extrapolated at very low densities. Of course, this is not completely true because we should use non-perturbative results, right? But in this case, we are assuming that this perturbative QCD has some constraints on the values of the critical density or the critical pressure, for instance. Okay.
More questions? So I guess everybody's hungry. We're a bit late, so we'll be back 15 minutes after the schedule, so 2:15. The speakers of the next session, please arrive a bit earlier to upload the presentations. Tulio, Christian, and Emmanuel, who's not here. So. Okay, so we'll be back 2:15. Thank you.